On my lathe, cutting a screw thread is a tiresome business. You have to set the change wheels in the gearbox, you have to manipulate the carriage and cross slide manually. There is no thread dial, so you have to keep the half nut engaged and reverse the chuck. After watching James Clow's video of his electronic lead screw, I realised all these things could be done automatically. The change wheels are replaced by a stepper motor and microprocessor. The lead screw and cross slide movements are orchestrated by the microprocessor. This project uses a Texas Instruments TM4C123 GXL microprocessor. The chuck speed is read by a rotary encoder coupled to the spindle via a gear train. The lead screw is keyed directly to the output shaft of a NEMA stepper. The cross-slide lead screw is coupled to a second NEMA stepper. The pitch and length of the screw is entered using push buttons. The tool is positioned to touch the workpiece and the lathe is switched on, which then automatically cuts the required pitch and length. Here we see the carriage moving a set distance, the tool being retracted from the workpiece and the carriage direction reversed, while the chuck rotates continuously. The tool is advanced and the next cutting pass is made. This pattern is repeated with no manual intervention until the required depth of cut is made. This is a cross-slide gearbox which mounts beneath the cross-slide and connects to the cross-slide lead. Now the important part about this is that it needs to hang down below the back of the cross-slide so that the cross-slide can still pass over the top and not collide with these gear wheels. At the back is a NEMA 17 stepper motor which drives a electromagnetic clutch which allows you to disengage the motor from the cross slide so that you can turn the cross slide dial as you normally would for parting off or facing or whatever you might want to do. The electromagnetic clutch is connected by this cable to the clutch switch, and the NEMA motor is connected to this by this cable to the microprocessor. This motor is capable of 200 steps per revolution or 1.8 degrees, but you can use a micro stepper driver to get 6400 steps, which gives you a very fine resolution if you want. I tend to use the 200 steps because when you're cutting a screw you want the tool to advance along the screw and very quickly withdraw at the end of its first pass, move back, move in, cut more thread, move out quickly, and repeat that pattern. The clutch gear is connected by two identical spur gears here, and the whole purpose of this is to be able to get this down below underneath the cross slide. All the bearings are running in these little roller bearings which have a 6mm thread, and I think they're 19 diameter outside. The whole thing is bolted together and mounts on the back of the cross slide through these mounting holes. Some more things to say about the cross-slide gearbox. It turns out that the lead screw on the cross-slide on my lathe is not running true axially, and the end of the lead screw is in fact rotating, describing a circle. So if you're trying to match it to this input shaft here, it's actually going around a bit like that. So what I did was to take a flexible coupling and join the two with that, and that actually takes up the misalignment of the two shafts. Now ideally you would take the cross slide apart and remachine the whole thing and put new bearings in and have it running true, but in the meantime this is quite a good way of dealing with that misalignment. This project originally started with a simple way of facing, and I used a straightforward DC motor here, which is 5,000 RPM but reduced to 10 RPM. That's a miracle of engineering in itself. It's reduction of what's that, 500 to 1 in a package that size is a pretty remarkable feat of miniature engineering. Anyway, when I started to correlate the cross slide with the lead screw movement, I obviously had to move to a stepper motor, and the first stepper motor I picked up was a NEMA 17 motor. This one is about 25 Newton centimeters torque, or 0.25 Newton meters torque, and it really wasn't adequate to move the cross slide against the various frictional forces in the cross slide. They do a second, more powerful motor, NEMA 17, which I didn't realise at the time, but this one is, I think it's about 50 Newton centimeters, or half a Newton meter, and this is much more suitable for the task in hand. So this is the 50 Newton centimeter NEMA motor on the back of this. One of the problems with this gearbox is that it has to be scrupulously clean, because any chips in these cogs is going to spell disaster. There's a very small backlash. Those teeth engage very closely, and even small chips is going to be a disaster for this. I haven't really found a very good way of dealing with this. At the moment I put the whole thing in a polythene bag, and with a few holes in it, and that does the job, but I'd like to have a more professional way of sealing this whole assembly so that chips are kept out of it. Okay, I think that is about all I have to say on the cross slide gearbox. So we'll move over to the lead screw gearbox, in effect. Stop. Okay, this is the lead screw gearbox and the microprocessor assembly. On the front is the rotary encoder for the chuck spindle, which engages with a gear train in a 1-to-1 ratio, so this reflects the chuck RPM 1-to-1. This spindle here engages with the lead screw with a keyed shaft. On this side we've got two BNC connectors for monitoring the motor pulses with a oscilloscope, an on-off switch, and a forwards and backwards push button switches. On the back, I can get it round. No, I can't. On the back we've got a 12 volt power supply, which is rated at 3.2 amps, which is more than adequate for the sort of power you're looking at on this project. It turned out that the stepper motor drivers got pretty hot, and I put this fan in to cool them. Over on this side we've got a connector for the cross slide motor. On the top we've got an LED display and two buttons, which this one is used for setting the pitch of the screw in millimeters, and this one's for setting the length of the screw. So by pressing this one We can go up to whatever desired pitch, 1.25 say, and we can set the screw length, which is 15 at the moment, but you can cycle through different lengths. So if we go to, say, 10, the first 4 digits on this display actually is a tachometer which reflects the speed of the chuck, and the lights above it there, when they come on, mean that the carriage is in fact going backwards. When they're off, the carriage is going forwards. When they're on, the carriage is going back. So if we actually power this thing on by switching on here and engaging the clutch, the electromagnetic clutch in the cross-slide gearbox, as we rotate the chuck effectively, the cross-slide is winding out the tool away from the work. The lead screw advances the 15mm we programmed in, and when it gets to 15mm, the cross slide winds the tool back into the workpiece. So it just goes on effectively doing that until you've cut the desired screw depth. So finally we get to see the result of all this effort. It's always satisfying to see the results of your project come to fruition. Here we're cutting a fairly large diameter aluminium tube with a 1mm pitch thread, and I think the length is about 20mm, 25mm. If there is any interest in this project, I have some drawings, especially of the cross-slide gearbox and the computer code for the microprocessor that I can publish. Of course, the gearbox is designed for this particular lathe, but the overall pattern probably suits many of the small Chinese lathes found in hobbyists' workshops. The computer code is set up for the common metric pitches, but can be easily extended to cut at any pitch. This project is really open-ended. Having got control of the lead screw and cross slide with the microprocessor, machining arbitrary shapes should be possible with programming. The first shape will be a taper. The simple push-button controls used so far will probably be unsuitable for entering more complex parameters, and a computer interface will be necessary. Some might say the time and effort involved buying a CNC machine would be far better. They may be right, but this is a hobby and time has no cost.